Take a look at this diagram of a hot-boiled egg. Heat transfers to the air right next to the shell, making that air expand, become lighter, and rise upward. We see the exact opposite effect here. With a cold can of soda, the adjacent air cools, becomes denser, and sinks. This invisible cycle, moving fluid continuously without a fan or a pump, is natural convection. To calculate the total heat transfer for either scenario, we use Newton's law of cooling, which is this equation here. We take the surface area, multiply it by the temperature difference, and then multiply by h. But h, the convection coefficient, is the tricky part. It is usually the missing variable, and finding it requires a specific 5-step mathematical pipeline. Because there is no external fan forcing air over the surface, the value of h relies completely on the fluid's own physical properties and how it naturally moves. Let's walk through the exact steps to lock that number down. Step 1 is finding the film temperature. As this diagram shows, the temperature changes gradually across the fluid boundary layer. To look up the correct fluid properties in your textbook tables, you need the exact average between the surface temperature and the ambient room temperature. Next, you evaluate how much that fluid expands when heated. That is represented by the volume expansion coefficient, or beta. For an ideal gas like air, beta is simply 1 divided by the temperature. But here is the critical rule. The temperature T used to calculate beta must be the film temperature converted to absolute Kelvin, not Celsius. Forgetting that conversion is the most common mistake students make. If you leave it in Celsius, the expansion coefficient is wrong, and the entire heat transfer calculation breaks right at the starting line. Now we move to step 3, understanding the forces inside the flow. This diagram of a warm fluid pocket illustrates the physical battle happening near the surface. The Grashof number compares the upward buoyancy force against the downward viscous friction slowing it down. We take that Grashof number and multiply it by the Prandtl number to get the Rayleigh number, shown in this equation here. The Rayleigh number represents the overall strength of the buoyancy and heat spreading effect in the fluid. That Rayleigh number dictates the flow state, which we use to find the Nusselt number. As this diagram shows, the Nusselt equation takes a different path depending on whether your flow is smooth and laminar or chaotic and turbulent. For a laminar flow, the exponent n in our equation is 1/4. But if the Rayleigh number is high enough to trigger turbulent flow, that exponent shifts to 1/3. Identifying that threshold between laminar and turbulent allows us to select the precise mathematical formula needed to evaluate the heat transfer rate. The shape of the object also controls the equation. As we shift from a vertical plate to a horizontal plate to a cylinder, the constant c and the characteristic length Lc change entirely to match the specific geometry. Let's pause and test those initial steps. We have a vertical plate at 100 degrees Celsius in a 20-degree room. Pause the video and calculate the film temperature in Celsius, then find beta for the air. First, we find the average between 100 and 20, which gives a film temperature of 60 degrees Celsius. Then we add 273 to convert to Kelvin, giving us 333 Kelvin. So beta is simply 1/333. Getting those initial property evaluations right and pairing them with the correct shape geometry guarantees your accuracy as we move into the final calculation. This brings us to step 5. This animation shows how we take the Nusselt number we just found and rearrange its equation to isolate our missing variable, the convection coefficient, h. With h in hand, we plug it right back into Newton's law of cooling. Here is the complete workflow to screenshot. Find the film temperature, get your properties, remembering Kelvin for beta, calculate the Grashof and Rayleigh numbers, choose the proper Nusselt equation based on the object's geometry, and finally, calculate Q. By strictly following this mathematical sequence, the complex, invisible mechanics of natural convection become a predictable, highly solvable engineering process.